Hey everyone, let's see, today we're going to talk about vectors. It's very possible that you already learned about vectors in some physics class or even a previous math class, right? So some or all of this may be review for you. So let's get started. A vector. So a vector, as you I'm sure learned, it's this object that has two different values associated to it, right? It's got a direction and a magnitude, right? So a vector is a quantity, or an object, maybe it's a better word for it, that has both direction and magnitude. Now, so vectors show up in physics, right? They represent various things like velocity, right? When you are traveling, you're traveling at a certain speed in a particular direction. So a vector is exactly the kind of thing, or is exactly what you want to capture that, right? That there's a direction and a speed. The speed is the magnitude. Force, right? You have so many pounds pushing in this particular direction, right? That's another example of a quantity, a phenomenon that for which vectors is the right way to describe. So we represent them geometrically. So we represent vectors geometrically as directed line segments. Well, okay, directed line segment, that's just a fancy way of saying arrows. And so the way we do this, right, the direction, so directed line segments are arrows in, and we're going to be working in both R2 and R3. Right, so we will have to, in some cases, do separate descriptions of vector manipulations in R2 and R3. Right, so where the length of the arrow indicates the magnitude. And obviously the direction of the arrow indicates the direction, right? So here's the idea then, right? There's an example of a vector. Let's call that vector u. Here's another vector v. We often, in the book, vectors are represented or written using boldface type. I'll put a little arrow over that to indicate that we're talking about a vector. So if we have, so there's a couple of examples. So if we have a vector like this, let's say vector u, we may or may not care about the starting point and the ending point of that vector, right? So this vector A, that's called the initial point. B is called the terminal point. And the notation, if we want to talk about the vector, the directed line segment, or the vector that goes from A to B, then the notation in that case, right? All right, we are talking about the vector that goes from A to B. Vectors are equal if they have the same direction and the same magnitude. And so this notion of equality is going to be important. And so here's the idea, and I'll bring this up again in a little bit. Let's take that vector right there, and let's take that vector right there. I didn't quite get them lined up perfectly. So what I want to do is I'm drawing two different arrows that, if I did this correctly, they have exactly the same length and they're pointing in exactly the same direction. So in this case, let's call that one U and that one V, right? They're not the same arrow, right? This one starts here and ends here. This one starts here and ends here. But if they have the same length and the same direction, right? Same magnitude and direction, then we say that they're equal, even though they emanate from different points and they end at different points, right? As vectors, they are the same. There's a zero vector. That's the vector, well, it has no direction, right? And it has length 0 or magnitude 0. So the zero vector is denoted using a boldface 0. Okay, so now this idea of having vectors that are equal if they have the same direction and magnitude, so that we associate or that we consider, right, these two vectors to be exactly the same, they're equal, right? But I mean, but they are different arrows. So here's the idea: they are the same vector coming from different places. What we call this is the same vector being represented differently, right? So a representation is a choice of starting point and ending point for a particular vector. So let's say if A is the point A1, A2, and B is the point B1, B2, then the vector U with representation as the directed line segment from A to B, with representation AB is, and so the way we do this is we use angled brackets, not parentheses. So we will indicate our vectors using angled brackets, and it will be B1 minus A1, comma, B2 minus A2. And so the picture, right, here's my point A, here's my point B, and then the vector that goes from A to B, right, is written in angled brackets this way right here. I guess I should, I should have labeled this part A, right? This is the formulation when we're working in R2, and so continuing on with this definition, there's going to be a part B that talks about vectors in R3. So part B, if it's going to be all the same words except A is going to have 3 components and B is going to have 3 components. So if A equals A1, A2, A3, and B equals B1, B2, B3, then the vector U with representation as the directed line segment from A to B is, and so we're going to write it U, and now it's going to have 3 entries inside the angled brackets. So it'll be B1 minus A1, comma, B2 minus A2, comma, B3 minus A3 inside the angled brackets. And now the picture is the same, except now we're doing this in R3, right? So we've got, here's point A, here's point B, and there's our vector U. So the thing to be aware of now is that every vector has multiple representations. In fact, it's got an infinite number of representations. So let's just say note that every vector has multiple representations, right? Every time you choose a new starting point for your vector u, you get a new representation, but each one of these is exactly the same vector, still the same vector u. Now, if you're in either R2 or R3, there will then be a representation of your vector that emanates from the origin. Right? And that vector has a special name, or that representation has a special name. It's called the position vector of the vector u. Right? So the representation that emanates from the origin is called the position vector. So the representation of the vector u with, or let's just say, I'm just going to say emanating. All right, so with initial point equal to the origin. I guess I should say with initial point. So with origin, or with the origin, as its initial point, is the position vector. And we will need to refer to the position vector quite a bit. We've said that the magnitude of the vector needs to correspond, or we represent that using the length of the arrow, and so we should be able to compute that by just using the distance formula, right? So, so two parts here for both R2 and R3. So the length, or magnitude, so these two things get used interchangeably. These two words get used interchangeably. Of the vector u equal to AB is, oh, and I need to check one thing real quick in your book to see, oh yeah, they just use absolute value bars. Okay. Yeah. So this is, and so it'll be written absolute value bars around the vector. That stands for the length of the vector. Don't think in terms of absolute value, though. And so this is square root of a squared plus b squared. And then for part B, the length or magnitude of the vector u, now if we're doing three components, A, B, C, is, once again, the notation is absolute value bars around a vector. Don't think of that as absolute value. You got to remember that this is the magnitude. And so, once again, we use the distance formula, a squared plus b squared plus c squared. Now, I'm claiming that we're using the distance formula, so let's do it in R3. What I'm doing then is I'm looking at the position vector. I'm starting at the origin and looking at the representation of the vector. All right, so here's my vector u that goes from the origin out to here. And so how do you measure distance? Well, it'd be a minus 0 quantity squared plus b minus 0 quantity squared plus c minus 0 quantity squared under the square root. And so this is exactly the distance formula, right? We're just measuring the length of that arrow. Okay, so as an example, so let's let u be the vector from the point 1, minus 1, 4 to the point 2, 0, 3. Find the length. And I kind of just go interchangeably between length and magnitude. They mean exactly the same thing. So let's find the length of the vector u. Well, so what we have here is a representation of a particular vector u. And so how do we get u? U is in angled brackets, so it's always going to be head minus tail. So it'll be 2 minus 1 for the first entry. It'll be 0 minus negative 1, so positive 1 for the second entry. And it will be 3 minus 4, all right, so that'll get us a minus 1 for the third entry. All right, so you always subtract head minus tail. Now, if we want the length of u, that's going to be the square root of 1 squared plus 1 squared plus minus 1 squared. So 1 squared plus 1 squared plus minus 1 squared. Okay, and so the length of our vector u is square root of 3. When you have a vector, there's certain operations you can do with your vectors. So now let's talk about some vector operations. The first one, called vector addition, all right, so if you have a couple of vectors, you can add them together. And so let's say if we've got u equal to the vector, what am I doing? Oh, let's call them u1 and u2. So u is the vector u1 comma u2. I need a sentence here. If u equals the vector u1 comma u2, and v equals the vector v1 comma v2, then we can create a new vector u plus v, and that's just going to be, we'll do the obvious thing, add the first components and add the second components. Right? That creates a new vector. And I guess, you know what, let's call this, I need to do it in both 2 dimensions and 3 dimensions. So here's our vector addition. Let me just make this look a little bit nicer. So vector addition. And then part A is the 2-dimensional version, and then I want to write down the 3-dimensional version next. So that's going to go right here. So if u is the vector with 3 components, u1, u2, u3, and v is the vector v1 comma v2 comma v3, then u plus v is going to be the obvious thing, u1 plus v1, comma u2 plus v2, comma u3 plus v3. So that's the sum of 2 vectors. And there's a nice geometric way to picture vector addition, whether you're in R2 or R3. Here's what you can do. All right, if you have u like this, choose the representation for v that emanates from the tip of the arrow of u. Right? And if you do that, then u plus v is the vector that completes the triangle. Right? So there's our interpretation of vector addition, right? Line line v up at the tip of u, or if you want to do it the other way around, put a v here, line u up at the tip, and the completion of the triangle, that gives you the sum of the 2 vectors. Okay, so there's our first operation. There's a second operation that's called scalar multiplication. And once again, we'll have two parts. So, so if u equals u1, u2, then if we take any constant, c times u is going to be the vector c u1 comma c u2. And then scalar multiplication in 3 dimensions. So if u is the vector u1, u2, u3, then do the obvious thing, multiply each component. C times u is c u1 comma c u2 comma c u3. Scalar multiplication has a geometric representation or geometric way to view it also, right? So if you have your vector u like this, then depending on the value of c, right, c times u is going to look different. But scale, you should think of this scalar multiplication, it scales it. So scalar multiplication is a process of stretching or shortening. And so c times u will look like this. It makes it longer, pointing in the same direction in the case that c is greater than 1. If c is between 0 and 1, it will shrink it down. I don't want to write all these possibilities, but if c is between 0 and 1, it shrinks it. If c is negative, it makes it point in the opposite direction. All right, so here is c times u in the case that c is less than 0. Right? So it's a shorter or longer version of u pointing in either the direction or diametrically opposed depending on the values of c. Right? A little bit of notation. So if we write minus u, this means, so this has meaning, it means minus 1 u. So it's the vector that has exactly the same length as u, but is pointing in the opposite direction. And so then we can define this, u minus v. This means u plus the vector minus v. So for example, let's say that, so u is the vector 1, 2, and v is the vector minus 3, 5. So then we could do 2u minus 3v. Kind of combining all these operations that we've got. So what this means then is, okay, so 2u is a 2 comma 4 minus, let's see, 3 times negative 3, 5 would be a negative 9, 15. And so this becomes the vector minus 7 comma, oh, no, sorry, that's a minus, so 2 plus, that's a positive 11, sorry. So 2 plus 9 is 11, 4 minus 15 is negative 11. Yeah, there we go. Now, these vector operations have certain properties, and so I'm going to write these down. These are not ones, I don't think you need to memorize this right here. These are the kind of things that we kind of just do in our sleep. Right? So I'm just going to write down a list of properties here. So these are vector properties. Properties. So the first one, it doesn't matter what order you add vectors, right? So vector addition is commutative. The second property, if you add the 0 vector, nothing happens, right? So u plus the 0 vector is u. Associativity, remember that property? It's where you can slide parentheses around. So, right, these two, it doesn't matter which order you do things, right? You can add u plus v, get a vector and add w, or take u and add it to v plus w, you get the same result. For u plus, or actually, well, let's do u plus minus u. Obviously gives us the 0 vector. Scalar multiplication is distributive, so c times u plus v is cu plus cv. And it's actually distributive in two different ways, so we can also do c plus d times u. And that will be equal to c times u plus d times u. C d times u is equal to c times du. So this is sort of an associative property with respect to scalar multiplication. And then one last property, 1 times u is equal to u. So these are properties that you are free to use whenever needed, right? And they will show up. They just sort of simplify the arithmetic involved in dealing with vectors. A couple more topics or concepts to talk about here. So there are what are known as the standard basis vectors. And this is stuff that you especially make use of in physics. So I need to give you the 2D and the 3D version. So in R2, I is the vector 1, 0, and j is the vector 0, 1. And then in 3D, so in R3, we have I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. Now, what's the point? In R2, any vector can be written in terms of I and j. And in R3, in 3 dimensions, any vector can be expressed in terms of I, j, and k. So the point in R2, any vector can be expressed in terms of I and j, and in R3, any vector can be expressed in terms of I, j, and k. And this is what you typically do in physics, right? Most vectors, instead of using angle bracket notation, they use the ijk notation. And so we will need to be able to go back and forth. I tend to use the angle bracket notation, this more mathematical notation, but in your physics classes, you typically will use your I, J, and K. So what we want to do is get familiar and comfortable with going back and forth between those. So, for example, 1, 2, 3 is exactly the same as I plus 2j plus 3k. I try to remember to put the little angle or the little arrows over the top. In your book, they'll be bold-faced. Oh, one last thing. So there's a definition. If the magnitude or the length of u is equal to 1, then u is called a unit vector. So u is a unit vector. Now, here's something that should be clear. Anytime if we have a non-zero vector, all right, so you take some non-zero vector. All right, so there it is. Let's call that one v. If you take some vector, there is always, as long as it's non-zero, there's always a unit vector pointing in exactly the same direction. I think this should be obvious, right? Even if this is length 57, there is still a unit vector that points in exactly the same direction. So let's just say note, and we want a way to find that. So note, if v is not equal to the 0 vector, then there is a unit vector u in the direction of v. And who is that? U is found by doing 1 over the length of v times v, right? So it's going to be a scalar multiple of v, and how do you get the right length? You just divide by the length of v, right? So guaranteed, this produces a unit vector that points in exactly the same direction as v, right? And we'll need this formula, we'll need this fact later on. Okay, so that's a good place to stop. So we will see you next time.